All right, in this video, what's up, y'all? How you doing? In this video, we are going to talk about improper integrals. Don't bother writing all this down yet because we're going to kind of cover it as we move along. But I do want to talk about what an improper integral is before we go into actually doing that. An improper integral is an integral that involves infinity. It should be pretty obvious that these three and this one here involve infinity because there's infinities in the bounds. Integral from 1 to infinity, 1 over x squared dx, 1 over root x dx, x e to the negative x. All of them are going from 1 to infinity or 0 to infinity. So they clearly involve infinities here. Same thing with this one. Then, with these guys, it's not quite as clear that they involve infinities, but they do. Notice these bounds, 0 and 1, those x values. If I plug the 0 into this equation right here, I get 1 over 0. And remember, 1 over 0 is undefined, but it goes to infinity. As the limit, as x goes to infinity, 1 over x, as x goes to 0, 1 over x goes to infinity, or 1 over x squared goes to infinity. As x goes to 0, 1 over root x also goes to infinity, right? So these two involve infinity in a way that's a little less obvious than these two. So there are sort of two steps in general. They've got like sub-steps, I guess you could say, that improper integrals require. One is that you actually recognize that we have an improper integral. So with these guys, it should be easy. This one, clearly, a little bit more work, but not that bad. And then the second step is simply to use good limit notation. Remember that infinity, it's not a number, and it cannot be treated like one. I need to treat infinity as something that numbers go to, not as a number itself. And that's the whole reason we have limits. So I will talk about that as we go through and we do these examples, and I'm just going to jump straight into this one right here. Actually, before I do that, I'm going to go ahead and do some Desmos talk. 1 over x squared. So we were looking for the integral from 1 to infinity. That would be the area from here all the way out to infinity. You see this thing goes down, right? So maybe it's bounded. And then the integral from 0 to 1, which would be the integral from here to here under this red curve. 1 over root x. Notice it's got a similar shape. They actually hit each other at 1, but then you see that the blue curve is above the red curve. So say the red curve was a number, the blue curve would be a bigger number. Then I've got x e to the negative x. That's this green one. You can see that it's, it looks like it's probably smaller than the red, but we can't really tell because it goes over at some point. And then we're not going to talk about the x at the end yet, but I just want you to see that these are the graphs of the three functions that we're worried about primarily. And they all have a similar shape in that they hug the y-axis and then they hug the x-axis. So the potential of going to that infinity is there. So the integral from 1 to infinity of 1 over x squared dx, that would be, there's 1. If I were to go all the way out like that, all the way out to infinity. Now, this would keep going for forever, right? But notice it's getting closer and closer and closer to the axis. If I were to do the integral from 1 to infinity of x squared dx, that's going to do what's called, it's going to diverge, right? The answer to that would be infinite because the area under x squared, actually I should start at 1, say that's 1. The area under x squared, that's going to go to infinity, right? Clearly, that is an infinite amount of area. But, and this seems weird to everyone when we do it at first, if I have a function that asymptotically approaches the x-axis, there's actually a chance that this green area here is finite, which is a pretty wild idea, but I think you'll see mathematically why that can be true as we go through some of these. Not all of them are gonna come to a number. Some of them will be infinite amounts of area, but some of them are finite and becomes really important as we move along in calculus. So the key here is simply, mostly just to use good limit notation, as I said, as I said above there. So I can't treat infinity like a number. normally we have numbers in our bounds. So anytime I have an infinity, I need to just use limits. So what I'm going to do is write equals the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. And notice now b is a number, and I'm looking at the limit as that number goes to infinity. You may say, why did you choose b and not a? Well, we usually talk about integrals from a to b. So if it's the lower bound that has an infinity, then I will use a. If it's the upper bound, then I'm going to use b. So let's go ahead and work this out. At this point, I just leave the limit notation. And then I'm going to go, all right, so let's integrate that. The integral 1 over x squared, well, that's negative 1 over x. And I got to evaluate it from 1 to b. Okay, so let's keep going here. That is the limit as b goes to infinity of, okay, I got 1 over b negative minus a negative 1 over 1. Close. All I did was plug in my bounds the way we normally do. From there, this is, I'm just going to rewrite it here so you can see it a little bit because it's got too many negatives and stuff, right? I can reorganize this and say this is the limit as b goes to infinity of a positive 1, that is the double negative here, and the fraction just being simplified to a 1, minus 1 over b. And now, this is a spot where this thing actually converges. I get a number. Look, 1 over b. What is the limit as b goes to infinity? Well, you got to ask yourself, what's 1 over a big, massively, infinitely big number, right? Well, you could go 1 over 9999. What does it go to as that 99999 gets bigger and bigger and bigger? It goes to 0. So this piece right here goes to 0. So what do I get? I get that this is 1 minus 0, which is 1. And that's pretty wild. Why is it wild? Because this green area under this graph, and notice you notice our window going from 0 to 8, 0 to 12, right? But this green area, if I go out for forever in that direction, it's just 1, and that's kind of wild. And by changing the function, I can get different areas, or I can get an area that is not a number and instead goes to infinity. So let's do some more here. Okay, next example is going to be the integral from 1 to infinity of 1 over root x dx. So I've got the graph of 1 over root x here. It's blue, and it's on the same scale as this one up here. So you should see that it's a little bit bigger than this red graph up here that we just said the area under is 1. Right? So this one right here, it does go to 0. It does asymptotically go to 0 as we move out along the x-axis, but it doesn't go quite as fast as this red graph. You can see that here in Desmos, where I've got the red graph as 1 over x squared, and we found the area from here out to infinity. And the blue graph is 1 over root x, and you can see that it is much larger, but do notice that if I zoom out, that they both go flat out asymptotically to 0, right? They are both very, very, very small functions. So let's go ahead and calculate the integral. Same process here as with the previous one. What we're going to do is use limit notation. It's the limit as b goes to infinity of the integral from 1 to b of 1 over root x dx. So that is going to be, I can integrate that, but I got to keep my limit first. Don't drop your limit notation. 1 over root x integrates to 2 root x. You should be able to do that. I'm going to evaluate it from 1 to b. That gives me, again, keep the limit notation. Limit as b goes to infinity of 2 root b minus 2 times root 1, which looks like 2 times root 1. There we go. So 2 times root 1, that's just 2, but this gives me the limit as b goes to infinity of 2 root b minus 2. So this is what I call divergent, which makes the integral above divergent. What do we mean by divergent? Something that diverges is something that goes away, right? So a divergent integral is something that goes away from an actual number. It goes to either infinity or to negative infinity. Why is that? Well, if I take the square root of a really large number, it is still a really large number. And as the numbers get larger, as b gets larger as b goes to infinity, then this term right here also goes to infinity. We don't say equals infinity because saying equals infinity would be like treating infinity like a number. So once we get to a spot where the limit would go to infinity, right, then we write divergent. Remember, root x looks like this, right? Well, maybe it flattens a little bit, or it doesn't go up as much, as steeply. It does continue to go up, and that's the idea of like root 500. Well, root 501 is going to be bigger. And if I were to look at root 9999999, if I were to add 1 to that, its root would be bigger than the root of that however many nines. So this thing goes to infinity. Therefore, the integral is divergent. And that's sort of significant because if we go over to what that tells me is that if I start where both of these intersect at 1 and go out to the right and take the area all the way out to infinity, the blue graph, that one, it diverges. It goes to infinity. It has an infinite amount of area. But the red graph, that one, it's finite. That area is actually just 1. So the question that comes up next, these are both kind of the same form. When would this graph transition? Like if I were to change x squared to maybe 1 over x to the 1.5 or 1 over x to the 1.2. When would those converge and when would those diverge? And we're going to get into that soon. Actually, I've decided to talk about that now. So this is important for where we're going. The integral from 1 to infinity of 1 over x to the n dx, where n is greater than 0 and is positive. What's the n being positive mean? It really just means this x is in the denominator. Because say I had 1 over x to the negative 1, it would just be 1 over x, right? And that, I think clearly, if you think about the area under x, y equals x, boom, 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 that's going to be infinite. So the question is, or the observation here is, if n is equal to 2, then the integral, let me just call this I, then I equals 1. It converges to 1, as we saw in this first example here. Because remember, that was x equal to, or n equal to 2. 1 over root x, well, that is n equal to half. So if n equals 1/2, then I diverges. It goes to an infinite, uncountable value. So the natural question that comes up, and I want you to think about this, and I think that if you can think in your head about how power rule works, and when integrating, we add 1 to a value. So my question becomes, for what values of n does I converge, which means it goes to a number. It could go to 1, it could go to 20, it could go to 30, 300, it could go to a million, but still converging. For what values of n does I converge versus diverge? And that becomes super important as we move along. So you can see here, I've written out a handful. Don't bother writing all these down. Just think about it, okay? 1 over x squared, 1.5, 1.001. This would be 1. This would be 0.9. This would be a half, a square root, a cube. Which of these would give me something that would go to 0 the way that this one did, the way that x squared went to 0, because I had that b, that limit in the denominator, and which would not go to 0 like this one up here, that square root? Just think about it.